Alrighty guys, let's go ahead and get started with our scientific notation and metric conversion notes. So I first want to talk about why we need and use scientific notation. Scientific notation is used because it's a lot easier and shorter than writing all those zeros with those very big and small numbers.
The basic form for scientific notation is going to be the following. We're going to say m times 10 to the n. And I'm going to tell you what m stands for in a sec. So m just stands for any number 1 through 10. N is going to stand for the number of decimals. So let's take a look at this a little bit further. What does it mean if the n is positive? So right here, we can see that our n is the exponent. So it's asking, what does it mean if we have a positive exponent? Well, if we have a positive exponent, the original number is bigger. And that means that we're going to move to the right, meaning that our m, the number 1 through 10, is going to get bigger and bigger and bigger. Now let's take a look at the other side. If n is negative, well, if n is negative, that's going to mean that the original number is smaller, and we're going to move to the left. So in other words, if we start with a number 1 through 10, it's now going to be a decimal, essentially, 0.000 some number. And we'll do some examples on the next slide. So our first example that we have is converting to scientific notation from a decimal. So first thing we want to do is find our base number. And remember, we just said that that was m. Then we want to count the number and direction of decimal places needed to get from your base number to the original number. So here's our first example. We have 2,500,000. So what I want to do is I want to see my decimal right here, and I want to count to the left how many spaces I move. So I go 1, 2, 3, 4, 5, 6. That means that 6 is going to be my n value. And my m value, like we said, is a number 1 through 10. That's going to be 2.5. So I end up with 2.5 times 10 to the 6. Again, this 6 came from me moving my decimal from the end all the way over to the beginning. I want to move my decimal until there's only one digit in front of it. Let's take a look at number 2. Number 2 is 0.00099. I'm going to do the same thing, except this time I'm going to move my decimal to the right. So 1, 2, 3, 4. I want to make sure that there's a number 1 through 10 to the left of my decimal, and that means that I would have to move it 4 spaces to the right. Because I moved my decimal to the right, it means that my n value is negative. So I would end up with negative 4. So 9.9 times 10 to the negative 4th. And again, I got that negative 4 by moving my decimal to the right 4 spaces. So if we take a look at our first example here, we have 5.67 times 10 to the 8th. We want to convert this from scientific notation to decimal. So what I recommend we do is we rewrite our number here, 5.67, and then we have 10 to the 8th, so that just means we're going to take this decimal place and move it over 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. So here's our decimal now. And then any little hump that we have that doesn't have a number in between it, we're just going to fill in with a 0. And that's all there is to it. So that means that our final answer should look something like this. 1, 2, 3, 4, 5, 6. Go ahead and add my commas, and I end up with 567 million. Let's take a look at the next one. This one we have 7.89. And if we notice, our exponent is a negative. So that means that we're going to move our decimal to the left now. 1, 2, 3, 4, 5. Put our decimal back down and then fill the humps in with zeros. So now we should end up with decimal 0.0000789. Let's move on for some more practice. First one is 3,000. We want to convert that into scientific notation. So to do that, we're going to take our decimal that's right here and move it over. 1, 2, 3, boom. because we moved the decimal over 3 spots, that means that our n value is 3, meaning that we would end up with 3 times 10 to the n. Well, we moved it to the left, so that's positive, so we end up with 10 to the third. Number 2, we have 2.000000, which means that we need to move our decimal to the left or right. We actually don't need to move our decimal anywhere because we already have one digit to the left. So this one, our n value is just 0, meaning that we would rewrite our number 2, multiply it by 10 to the n. Again, our n is 0, so it just looks like this. Number 2 is a tricky one that you might see again in the future. Number 3, take our decimal, move it to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this time our n value is 11, but because we moved it to the right, it is negative 11. Go ahead and write my number 4 times 10 to the n is negative 11. Next one we have is 10,001. Here's our decimal. Got to move it to the left. 1, 2, 3, 4. Moved our decimal 4 spaces to the left, so it's positive 4. So we have 1 point. Well, we have all these zeros, but then we have this 1. We want to make sure that we include any numbers that aren't 0 in our m value. So that would be 1.0001 times 10 to the 4th. Super important that we don't forget about this 1 here. Number 5. This time we're taking scientific notation and putting it into decimal form. So if we look, we have 8.598 times 10 to the 13th. That means that we're going to take this decimal and move it to the right. 13 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Fill all the little humps with zeros. We're going to have a lot of zeros here. So our final answer should look something like this. 8598. And then there should be 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If this problem alone doesn't tell you how important scientific notation is, then I don't know what else to tell you. Because this is very tedious writing out all these zeros, and it's a lot easier to see the number here. If I were to write out these zeros, I guarantee I would miss it a few times. Number 6, 1.00006 times 10 to the negative 5th. So let's write our number down here, 1.00006. And then to the negative 5th means that we're going to move this to the left. 1, 2, 3, 4, 5. Fill in with zeros. So now we have our decimal, and then we're going to write 0, 0, 0, 0, 1, 0, 0, 0, 0, 6. So this one is a super small number, and it's a complicated number because there's a lot of zeros in there. 5 times 10 to the 0th. Well, here's our decimal, and I got to move my decimal 0 spaces. So I'm just left with 5. And now we're going to look at the quantity, unit, and abbreviation. So the quantity we have is length, mass, volume, and time. And in this class, we're going to measure length in meters. The abbreviation for meters is going to be a lowercase letter m. Then we have mass, and mass in this class is going to be measured in grams or kilograms. And the abbreviation for grams is just a little g. Next, we have volume. Volume will be measured in liters, with the abbreviation being a capital letter L. And lastly, we have time, and time will be measured in seconds, with the abbreviation being a lowercase letter s. So if we look below, we have our prefixes, and the prefixes are just these letters that we tack on in front of our units. And it gives us some sort of value for those units. So for instance, we have KHD, and then here's our normalized units, so liters, mass, grams, DCM. And those abbreviations have the following quantities attached to it. So K stands for kilo, and that's going to be 1,000. H, 100, D, 10, and then the base units, liters, mass, grams, is just 1, deci, 1 over 10, centi, 1 over 100, and milli, 1 over 1,000. So as we move over, we get smaller and smaller. So let's take a look at some conversions really quick, just a nice little review. Jose ran 1,505 meters. How far did he run in kilometers? So we are given the value in meters, and we need to convert that to kilometers. Well, first, we need to think about what is the number that we know. Well, we know that Jose initially ran 1,505 meters. What is the number that we don't know? Well, what we don't know is how far he ran in kilometers. Does this cross the base of the metric line? If it does, we're going to need to do a two-step conversion where we stop at the base before continuing. So that baseline is what we talked about on the last slide, and that's that middle part. So right here, this is our baseline where it is just 1. So does the K cross the baseline? No, it's just on the other side of it. So since it does not cross the baseline, we don't need to do anything too crazy. Next, we're going to set up our conversion using dimensional analysis. And that's just a fancy way of saying converting units. So if we look, we start with the value that we know, which is 1,505 meters. We put that on top. Then we're going to multiply that by some ratio or fraction of units that will give us kilometers. We know that 1 kilometer is equivalent to 1,000 meters because we just saw that on our last slide, and it's something that's on our unit conversion cheat sheet. So because I have meters on top here, I should put meters on the bottom here. This way, when I multiply through, the meters on top cancel out with the meters on the bottom, and I get my final answer. My final answer should be 1.505 kilometers. So this first question asks us how many millimeters are in this many meters. Well, we have meters on top here, meaning that we need meters on bottom. We know that 1 meter is equivalent to how many millimeters? Well, if we look at our cheat sheet, we see that it's 1,000 millimeters. Meters on top cancels out with meters on the bottom. We just multiply through. We end up with 4,454.7 millimeters. Next one says how many kilograms are in 2,345.4 grams. So we have grams on top here. We need grams on the bottom here, which means we need kilograms up there. Kilograms are bigger than grams, so we know that 1 kilogram is equivalent to 1,000 grams. Multiply our way through again. We end up with 2.3454 kilograms. Next one says how many centiliters are in this many kiloliters. So this is going to require a two-step process. The first one is to go from kiloliters into regular liters. We have kiloliters on top. Let's put kiloliters on the bottom, regular liters on top. We know that 1,000 liters is equivalent to 1 kiloliter. Kiloliters cancel out, but we need to end in centiliters. Since we have liters on top here, we need liters on the bottom, meaning centiliters on top. How many centiliters in a liter? 100, 1 on the bottom. Now we can just go and multiply our way through. We should end up with 56.3 centiliters. How many meters per second are in 0.067 kilometers per hour? So we need a way of converting kilometers into meters. And the best way to do that is to know that 1 kilometer is equivalent to 1,000 meters. Kilometers cancel out, so now we have meters, so we're good on top. The issue though now is that we need to figure out a way to get rid of this bottom unit and convert it into seconds. Well, since we have hours on the bottom, we need hours on top here. And then we need a way of going from hours to seconds. Let's say that we don't know that. What we do know though is that 1 hour is equivalent to 60 minutes. So we can put 60 minutes on the bottom and 1 hour on top. Now our hours have disappeared and we're left with minutes, but we need to end in seconds. So luckily, we know that 1 minute is equivalent to 60 seconds. So we have minutes on the bottom here, means minutes on top. 1 minute, 60 seconds. Minutes cancel out, we're just left with seconds. So now we have the units we need, meters over seconds. All we have to do is just multiply our way through, and we find out that our answer should be right around 0.0186 meters per second.